Welcome to Accendo Reliability webinar series. This is Fred Schenkelberg. And today I want to talk about techniques, kind of getting into the details a little bit about what we do. Yet I'm not going to go into individual tools. Obviously, in an hour, I could spend a whole hour or more just on FMEA, for example. And Carl has great sets of tutorials and a book out on that topic. We could also spend lots of time talking about, say, accelerated testing and when and why to use that and how to design it and so on. So I'm going to break that up into various details. But the idea here is that there's a handful of things that us as reliability professionals really need to know as at the technique level, our technical prowess, so to speak, and a couple other things. And I'll get into some more details as we go here. Find my cursor. All right, now Carl Carlson, good friend of mine, and I have been doing a RAMS presentation for a number of years, and he's moved on to doing that with Chris Jackson. I think he did it first time last year with him. And one of the stories Carl tells is that when he first put together a reliability plan for a program he was assigned to, he went out and did a search of all kinds of standards and regulations and books and templates and everything he could find, and just listed every activity that he could find. Every acronym, every technique, every tool that he could find. And that just wasn't feasible or manageable, nor was it useful. So a very key concept that I want to keep in mind, and many of you have heard me say this before, is that you only use the tools and techniques and the processes that actually add value, right? The ones that are essential to me are the ones defined as the ones that help solve a problem or inform a decision or add value in some tangible way. Now, it's the outcome, the resulting behavior of those tasks and activities and techniques that we have. If we do an accelerated life test, yet it's 2 weeks too late to inform a decision as to whether to ship or not, that test report is only the paper it's on. It has no value beside that. The idea is that it's not the report that's important. It's the behavior because of that report. And we'll talk a bit more about this as we go on. And it's the resulting value. And you obviously have heard me say this over and over again. The other part of what we do, and it's a technique that is very difficult to stay focused on. And the problem is that we often focus on what we're doing and we're not willing to be surprised. We're not primed to spot the unexpected. The analogy I use, and I have been over the years a bicyclist and a road bike, and I'm acutely aware that when a car is pulling out onto a road, they might look directly at me and not see me and pull out anyway. And what the issue is that when all of us are driving and we look for oncoming traffic, we're looking for a car or a truck or a bus. We're looking for two headlights. And motorcycles often have trouble with this phenomena and they get clipped, and bicycles even more so. And so it's not that we don't physically see them, is that our brain isn't looking for that, so we don't see it. We're focused on looking for that big truck. That would be really a bad thing to pull in front of. And so part of the idea of a technique is priming ourselves to be able to see that bicycle coming, even when we're not looking for a bicycle. And I'll use that as an analogy, but we'll certainly talk about it some more. All right. Now, I know some of you have heard me talk about this before in other ones, but in your program, in your work, day-to-day work, how do you decide to do an FMEA or not, or a halt or not, or a test, an environmental test or not, or some other activity or technique, say prediction or a model or whatever. How do you decide what you're going to work on? And let me get a drink of water. Okay, I got one from Laura. Thanks. New product intro items always get a DFMA. You know, the key I pick up on there is new. I always call those the red flags. There's a new supplier, a new vendor, a new manufacturing technique, a new design element, a new invention, a new market. Pretty much anything new should get some risk identification of some sort, and design FMEA is certainly appropriate in many of those cases. I know that there's more than that, right? There's a handful of things that we go to commonly for certain circumstances, certain triggers. So what guides your decision process here? Right? Yes, most have legacy features. Yeah, and yeah, when something's different, it's worth looking at. I agree with you, Laura. Now, that's a concept that gets us in a rut. When the question is, how long will this last? We do an accelerated life test. Well, we really could do physics of failure if it's appropriate for that failure mechanism. We could do an FMEA, but maybe a fault tree analysis is more appropriate in this particular circumstance. If the top question is, how do we minimize the computer crashing, for example? That is a type of a situation where a slightly different tool may provide more insight and more interest. Another answer here is gap analysis. Yeah, part of what we do in how we decide what to do, and obviously you're in line with what Carl and I often talk about, is, well, what do you need to know, and what are your circumstances and situation right now? And so an accelerated life test may help you bridge that gap from, I don't know how long it'll last, to here's a study that will tell us how long it'll last, or give us a pretty good indication of how long it will last. So a gap analysis is also a good technique to use. So let's dive into this a little bit. You may have heard me hinting at it in that question, but the idea here is that a good amount of what we do is based on the decisions that are going to be made. And usually those decisions are by somebody else. The program manager, the design engineer, the manufacturing engineer, the operations manager, the simple decisions of, are we ready yet? Is it good enough? Is it meet all of our criteria? Will it work? What haven't we found yet? What issues are our customers going to discover? We often face a series of decisions in the product development process and in bringing a product to market that require us to make decisions in one form or another. Some are small and some are very big. And I've broken them down into a couple of ways that we interact with decision makers. And so let me dive into that a little bit. The first one is, in order for us to create a plan, to create a sequence of tasks that help us to inform decision makers, is we need to understand what's at risk. As Laura mentioned, is if most of your products are legacy and really aren't changing too much, well, you've got field data, you've got production data, you've got all of your internal information that gives you a pretty good idea of what's working and what's not working. And it gives you a pretty decent idea of what needs improvement. And so it's fairly well known what's happening. Then you bring on this brand new concept or new market or a new product platform. Now there's a lot more uncertainty. And I use the word risk here as uncertainty. It could be good or it could be bad. It's just that it's unknown, it's cloudy. And so the idea here is that when we start a program and all the way through it, many of the times the decisions that we're trying to make or others are trying to make involve ambiguity or uncertainty or fuzziness about what is known and not known. And so one of the early steps is similar to this gap analysis idea, is what do we need to know and what do we know? And then when the difference between those two things is a gap. And then we can use a range of different tools to bridge that gap, depending on the constraints and that particular question or decision that needs to be made. The idea is that if, and I ran into this in one of my assessments, this one program, one product development group would come up with a new product or an iteration of a product pretty much every year. And so one of the engineers that had been there for a while said that, you know, each year in October, we're supposed to launch a product. And in the last 20 years, according to the record keeping he had done, that they launched on time only 5 times. The other 15 times had a range of different issues with them, but they were on average a delay of a month. And that had a ripple effect, is once they delayed, say for 2 months, it took them even longer before they got back on schedule. So there would be a loss of resources to develop the new product, then it would be rushed, and then it would get delayed. And that cascade would go for 3-4 years until they would get a year they'd launch on time, and they might launch on time again, and then something would happen and push them back. And so what they were doing is looking at that track record and looking at their process, kind of like an FMEA, but on the product development process, in order to understand what was causing this. They did a root cause analysis, so to speak, on their development process to understand why there were delays in what was causing these things. And they made some fundamental structural changes to their processes in order to meet their demands. Now, one of the outcomes of that is after they shipped on time for 3 or 4 years, of course, then they added more features, added more constraints, tried to drive some cost out of it, and they got delayed again. They forgot their own lesson. The underlying point here is that a big part of the decisions that are being made can be informed by all kinds of things. And FMEA and hazard analysis and those kinds of tools help us to formalize and prioritize what we don't know and what we need to know. For example, if we have a high severity, high occurrence type issue, there may be uncertainty about how often it really occurs or how does it actually lead to a high severity type issue. Those uncertainties give it a higher score. And oftentimes, at least what I find is when we do these kinds of assessments, is it sparks some investigation or study or experiment to quantify, to better understand the amount, to reduce the uncertainty is what I really should say. But the hard part here is that we walk around and talk about failures all the time and what that means to our customers. And then we run into a program manager who just wants to ship it no matter what. Part of that is because we have a different appreciation of the risk that we're being faced with, right? So we may say, we're going to have a 2x the size of failures, number of failures in the field than we expected, according to our profitability and modeling and everything else. That's unacceptable. Now, there's still fuzziness as how accurate that projection is. And some people will say, well, that's fine, let's go ahead and ship. Others will say that's not tolerable, let's not ship at all. And that's what I mean by risk appetite. And the idea is that's part of the culture. Now, we often get a uniform approach to making decisions based on cost and time to market and functionality. Those are easier, as we all know, to measure on a regular basis, whereas future failure rate is fuzzier, has more risk associated with it. And so the idea is to calibrate what is the trigger points and what do we agree on earlier when we have time to think through it rationally rather than waiting to the day before launch and there's a lot of political pressure on us to launch anyway. Now, the risk profile, the risk appetite that we have, it may change depending on where we are in a program, yet it needs to be coherent and best if it's consistent across the organization. That helps us to answer the appropriate questions, to do the appropriate research and use the appropriate tools so that we can inform decision makers such that it helps them understand the risks and the uncertainties and what we know and don't know, and judge it accordingly in consistent manner. So the use of tools that help us identify and prioritize and manage risk are triggered by the desire to reduce the veil of uncertainty around making decisions. And so those decisions could be launch the product or prioritize resources. So a couple of ideas there for you. Now I'll find my cursor again. The other piece that we do with decision making is discover stuff, right? It's a seasoned program manager will recognize that when we're creating a new product or creating something that we haven't done before, is that it may fail in ways we don't expect. Right? If we're using a new material or a new manufacturing process or a new vendor, for example, is even though they say, usually the sales engineer, it's the same form, fit, and function. You'll have no issues compared to what you've been using. It's half the price, right? Well, that usually, from experience, that usually makes me question that and want to go figure out what happens. The other piece of this is that we do oftentimes during product development, we make prototypes or breadboards or mock-ups or simulations, and something might not appear like we want it to. Something might be glitchy. Something might show an intermittent failure. Something might just fail outright. And the hard part here is like looking for that bicycle, is we need to treat every anomaly as something that we can explore in order to be surprised or to understand something. The idea that failures are gold is a cultural thing again, and I keep coming back to that. The idea is that we don't do HALT just to find failure mechanisms, right? That's not the only tool out there to do that. Turning on a prototype for the first time is a form of a HALT, right? We're not step stressing at all, but we're applying power to it and seeing if it works. It's the same basic concept for obviously an electronics product. But the idea here is that if we find, and we have to be looking for and be willing to actually see things that don't quite work. And years ago, a friend of mine said, well, you reliability folks, you look at the world as a failure point of view. You're consciously looking for failures. I says, yes, that's what we do. And he says, a design engineer doesn't do that. We are looking at it from a success point of view. We want to create a design that will work. And so even though it's complementary, it's not the same view, and we have different sets of blinders on. And so recognize that not everybody sees a red light when it should be green as a problem. They just reset and drive on and get their task done, and they get the green light the second time, and then don't report this anomaly. And then we find out it affects 50% of our products in the field, and it's considered a failure by our customers. It's based on a real story. But the idea here is that we can deliberately set up protocols and evaluations and tests that look for what we don't know. But more importantly is our culture in the organization, our ability to recognize anomalies as useful and run that balance of not making that onerous to the organization so that nothing moves forward. It's more along the lines of celebrate those failures and let's see what's going on so that we can learn something. And then the last part about decisions is we don't often make those decisions, right? We influence people. And the idea here is that design engineers and program managers and senior management may all understand that reliability is important, may understand that what we're working on is critical, all these kinds of different things. Yet, if they're focused on structurally and individually focused on shipping on time, our influence may have little to no effect. And so part of this is our ability to build an understanding of the types of information we bring to the table and how that can be used. So if we just say, all right, we're going to use derating from now on, or stress strength calculations with a 2x safety margin, and we get a senior manager to say, this is the new policy, you have to do this, we'll get very little adoption of that and actual use of it, and plenty of exceptions and workarounds. If this actually helps that design engineer create a design that works the first time, so they don't have to redesign and troubleshoot and do all the tedious part of what I found most designers don't enjoy a whole lot, it actually adds value to them to use the derating guide. What I found, though, is that it has to be their idea, right? A lot of what we do is not dictate or enforce, or it's generally not effective as from a cultural point of view or an effectiveness point of view. The idea of what we do is through our interactions, our reports, our studies, our comments at staff meetings and all those things, that each and every single one of those things has to add value. And it has to add value in the eyes of that audience. They actually have to understand that if we did it in this other rated life test, then there's a 68% chance that the 2% tile of failures will occur with 90% confidence and blah, 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 blah. And we do this big mathematical, statistical jargon type stuff. We've lost everybody. If we interpret that result so that it interacts with the decision they're actually trying to make, then they know how to use that information. And so what we do has to actually add value, not in our view, but it has to add value to what they're trying to do. Shorten their day, reduce the risk, help them sleep at night, clarify a piece of information they've been struggling with, provide them guidance or tools that streamline what they're doing, or make it more understandable, those kinds of things. So a lot of what we do is focused on helping other people make decisions. And the trick here is something that we don't normally do as engineers, is that we need to build our trustworthiness, our influence through that trust. And so that's a key part of a technique that we should use, is to understand what's important to them and then bring content and information that helps them create value to what's important to them. And it's a fundamental technique, I think, in how you influence people as they're making decisions. All right, so I talked about a couple different skill sets there, and there's a number more that are in our body of knowledge and in our different day-to-day tasks and so on. So let me grab a sip of water. What would you consider as your weakest skill set when you consider all the different things we do or are asked to do as a reliability professional? Might not be a fair question for a Tuesday morning that actually feels a lot like on a Monday. And this is one, I'm going to bring up a couple of them. But one of the skill sets for me has always been a challenge, and I have to work very hard to understand formulas and apply them correctly and derive things and so on. And I find it over and over again when I do the CRE prep type courses, is the statistics and the math is tripping up so many people. But it's a fundamental technique that we have and should master, is we use math, and we have to. we have a range of different tools available to us, yet it's the understanding of math to such a degree that you can provide meaningful information with understanding and the ability to help others understand it. That's the critical piece of this thing. And so let's take a look at some of this in a little bit more detail. So we get piles of data, right? We get field data, we get prototype testing data, we get accelerated life test data, we get material strength analysis, we get vendor data, we get data. We got tons and tons of data. If we're in a factory, we get terabytes of data on a regular basis. If you have a statistician, give them all this data, ask them the right questions, and they can help you a lot. Yet, oftentimes we need to do this analysis. And the idea here is to let the data work for us, is right? Data in itself is just fodder. It's just the piles of numbers. We need to convert that into information, into something useful. And so the basic skills of what we get thrown into a lot of times includes, well, what question are we actually trying to answer? What are we trying to do with this pile of data, right? So if we have a field data coming back from customers, say related to warranty returns, well, in and of itself, it's just a pile of data. Yet if the question is, are we going to meet our targets for profitability based on warranty claims? Well, then we do a regression analysis, and we might do a projection to what's going to be for as products turn out to be a year old or whatever the warranty period is. Do we have enough spare parts? Well, looking at the overall system may not help us with that, but looking at individual replacements and types of failures that occur, if that's within the data, then helps us to do analysis at that detailed level. But the idea is that we have a wide range of tools at our disposal as reliability professionals. It includes statistics, doing comparisons or plotting or displays. A Weibull plot oftentimes is illuminating for so many people of what's going on with a time to failure pattern. But also just a simple Pareto chart oftentimes helps a whole lot if we can make it clean. My pet peeve is three-dimensional, just artificially three-dimensional, making the columns, the bars columns instead. And it throws off perspective, especially when you look at it askance. You try to tilt it and to feature this artificial three-dimensional thing, but I digress. But besides doing Weibull analysis, we also do a range of different kinds of regression analysis, looking for patterns or time series or all kinds of different things. Remember that there's a lot more than just doing Weibull analysis. But we also get involved with studies and surveys and all kinds of other data sets that talk about customer satisfaction and how important, say, reliability performance is in that overall customer satisfaction. We may be using a range of non-parametric tools to do that. The idea here is that a fundamental technique that we use is math, right? And it includes all kinds of ways to look at data. And part of this includes just playing with it, exploring it. Other times it's analyzing it to answer a specific question or provide a projection or results for a comparison. And so there's a lot to this data analysis is one aspect of the mathematics that we use. The other aspect of it that I see used very, very often is modeling. Now, modeling is not just the reliability block diagram, right? Or a system reliability availability type model or some sort like that. Those are certainly types of models we use, and we can influence or improve those by actually using the time to failure and time to repair distributions inside those things. But we also get involved with Monte Carlo techniques, and we get involved with Petri nets and a range of different modeling tools. In looking at systems and subsystems and even components in understanding how they work and don't work and what kind of patterns they're going to be used. But we also do a lot of modeling, especially in expensive products or low volume products where we really don't get 30 of them to go to the lab with and break. We may use mock-ups or coupons or pieces of a system that has the feature set that we believe is close enough to its application. And it's essentially a physical model of the element that we're interested in. And so we'll run tests, say, on a hinge with simulated forces on it that represent the actual forces. Or we'll add vibration, say, to a system to simulate or model the actual transportation vibration we expect to see. In some respect, those are models that we're using also. Now, another whole area, and it dives deeper into the mathematics oftentimes, is physics of failure. Those are sometimes rather complex models of how a failure mechanism manifests itself. Sometimes they're straight empirical, like the Norris-Landsberg model is the result of many, many observations of time to failure for different solder systems. And it happens to be a form of a function or a formula that describes that behavior rather well. And so while it's not from first principles, it gives us a model. Physics of failure, oftentimes the purist will call it that it's from first principle. What is the chemical behavior of this? What's the diffusion rate? How's temperature or amount of reagents and cross-sectional areas all impact the particular fundamental behaviors of this failure mechanism? But we use formulas and details throughout. And so I go back to that fundamental skill of understanding the math. And one technique for both modeling and for analysis is a lot of what if and playing. Now, as I mentioned, I struggle all the time with the mathematics. It's not intuitive to me in many cases. So I'll play with the formula. I'll stick something in Excel and, well, what happens if I increase this? What if I go to the lowest setting? What if I go to the highest one? How does increasing this factor influence the overall result? If I see something raised to the negative 1/3, okay, how does that influence the result? Let me play with that and change some of the numbers so I get a sense to how that formula works. We got the tools to do that pretty easily right now. One of the things to guard against and why I suggest that this mathematics is a critical technique or bundle of techniques that we need to apply is you can stick all kinds of numbers into a software package and get a beautiful plot out or fitted formula out. Without the understanding, you don't know whether that's the right model or not. It may be completely inappropriate, yet you get a nice plot. That's the hard part here, is the fundamental technique that we need to have is the understanding of the mathematics, of the regressions, of the formulas that we're using, including their assumptions and constraints, so that we can use them appropriately in using our mathematics in software packages or on a piece of paper, such that we can explain it in a meaningful way that others can use that information. And then presenting. And I'm using presenting as a very broad brush on all the soft skills, right? How we present the information. And I mentioned it earlier, is the fundamental piece of this is understand what question your audience has and what is their understanding, and how do you bring information to them so that they, one, see it, right, the bicycle, two, is they understand it, and three, that they can use it. So if any of those things break down, it's a nice presentation, but not very effective, not very useful, not very valuable. And so all the basic presenting rules apply for business. But the idea is that you need to really know your audience. And you've heard this over and over again when sitting down to create a report or a presentation. And if you don't know, go ask, right? If they don't know, then ask, why am I doing this? Right? It's an appropriate question. The idea is if you're providing information to somebody else is not useful, well, that's as much your fault as theirs, right? If it is perceived as useful by you and they don't perceive it as useful, then I would point to your presentation skills. Help them understand it, bridge that gap for them. And that's an essential technique that we have. All right, quick question. What's your favorite failure analysis tool? How do you like peering into what we don't know about something? I'm going to mention a SQUID. I don't know what it stands for, but it's a tool, and it has some microscope type of things uh, that allows you to visualize current flow. And it's a great tool if you have a trace current someplace that you don't, it's not in the circuit, but it's crossing two lines and it's not supposed to. And you can actually see, and it's enhanced, but you can see current flow. It is way cool. It's a fun tool. So 5 whys, Bayesian analysis, usually it's Weibull analysis. Okay, I like, range of tools. Fault tree. How about in the lab? What's your favorite? I like SEM is common these days. Not common enough, I think. There's a couple of different math tools here. Bayesian, Weibull, modeling is a fault tree. It's a great tool. Got to know some Boolean algebra to take full advantage of that. Microscope, yeah, sometimes just a simple microscope. I always like getting ones that have a reasonable magnification, but also have a camera feature on it. It makes for great reports when you have a beautiful photo of the failure mechanism going on. Analytics, okay, that's a good, right? One of the under pieces that I think is an essential technique for us is curiosity, right? Failure analysis is one way that we go after, well, what happened here? Why did this fail? Right? And 5 whys and a handful of other tools help us to get to that. But also how and what we measure, and then just the curiosity of asking the right questions, and that's the experimentation part. And so one of the things that I drive for all the time, let me see if I get my, I guess not, I don't have my drawing tool set up here today. I was going to underline, do not send to a vendor as your first response. If you have a failed component or a failed part or a failed piece of material or a bad batch, the over and over and over again, I'd say in about 70 to 80% of organizations I've ever worked with in one form or another, is their natural inclination is to take that bad stuff or bad item or failed part and send it back to the vendor. And 99% of the time, it takes too long and they get too little information back. And so it's not really a valid or a useful failure analysis process. I use 8D, 8 disciplines, or I've seen some people do 7 disciplines where they skip the party at the end. The idea is you're just asking the question, why did this happen, right? What happened here? What fundamentally occurred that led to this red light showing up versus a green light? Why did that happen? Was it software? Was it this? Was it that? So things like fault tree analysis helps us peel back at this thing and know where to go look. Sometimes in the lab with SEM or SQUID or some other high capital type equipment, or something simple like a magnifying glass or a microscope, helps us to understand the fundamentals of what's going on. And the idea here is that failure analysis doesn't have to be a PhD thesis every single time. But on those important projects, the ones that we really need to solve, it's worth the investment up front to get it right. And as you get more the knack of asking these questions, what's going on here, and we go through the litany of non-destructive testing, and then we start taking it apart in a destructive manner, we learn a lot. And there's a handful of tools and techniques and processes I've used over the years that have formed my, I don't know, I guess it would be called a spider sense of that doesn't look right. Let's take a look at that a little closer, right? Something is shaped in a way that is going to be a stress increaser, and I've seen cracks propagating right down that kind of structure before. Well, let's take a closer look at that. What kind of analysis can we do? Let's do a finite element analysis, or let's do some drop testing or vibration testing to see how this structure behaves, because my experience says that's a weak structure. Other ways that doing the failure analysis helps is that it gives us those cool pictures to show people that don't believe it. And so many of you have heard my story about we suspected the structure of mounting a circuit board vertically next to a large mass that was traveling horizontally was a bad idea. We thought, well, this circuit board is going to flex, and that flexing a circuit board is usually not a good idea. And to make a long story short, is we used the high-speed camera as we powered it up, and our intent was to see the amount of flex. But what we found instead was a component snapped off and twirled through the air and fell off, and then the whole thing stopped. All it took was that 15-second slow motion image or video to convince the mechanical engineers that they needed to fix that. We didn't even have to say anything. Sometimes our failure analysis, you get lucky and you see the failure happen as it happens, which we did in that case. And you've got hard evidence right there on camera. That was great. Other times it can be tricky, right? And sometimes they're fun. Sometimes they're just out of curiosity. You want to know, so you don't invest a lot into it, but you might pursue it. One that I got years ago was, what is squalene? And some of you have heard this story. It's a benign inert substance, but it was associated with corrosion on circuit boards. With a little bit of analysis and digging into it and a little more chemistry involved, we found that it was hand oils, the chlorines and bromines and other naturally occurring chemicals on your hand can initiate failures, but squalene is prevalent. And so the first analysis found that element as the dominant material that was present, but it was the subsequent elements and deeper analysis that found what was leading to the corrosion. So be curious, why did it fail? And sometimes it's cursory, sometimes it's just for your own interest in something to learn about, but most of the time is we need to solve it so that we understand it well enough that we can then actually design it out of a product. Now, in that process, right, and in the process of manufacturing, in the process of making prototypes, in the process of running tests or experiments, we make measurements, right? If the measurements are not useful or are not done well, right, it's garbage in, garbage out, right? So sometimes we need to go get some quick data. We go down to the production line, we handwrite a couple of measurements, we make some quick things, and we challenge an assumption, or we do a hypothesis and get some data to compare those things. Other times we do a more formal set of testing, and we create measurement systems or automated systems and so on that gather the data in a more coherent and consistent and lower error rate than normal. But the part of the process here of being curious is a technique, is that our observation can mislead us. If we're looking for a truck, we won't see the bicycle. So be careful with how you set up your measurements, is that they have the ability to detect what you expect them to detect, right? But also be prepared that if they give you an anomaly, that you don't write it off as just measurement error or randomness or a quirk in the measurement system, but it might actually be an underlying phenomena that you need to know about. If you set up and create measurement systems that minimize measurement error and measure the phenomena that you in an accurate or as clean as possible way, then those anomalies are more likely to be something that you really need to pay attention to. And they could be for the benefit or the detriment of your particular product. But the idea is that in order to make good measurements, we need to understand what exactly is it measuring and how does it behave, say, with temperature fluctuation or material changes or operators that interact with that system. Sometimes it's just straight measurement error. Other times it's a surrogate measurement for something that we're really interested in. And there's a few steps of logic and physics that intervene between these two things. So as you make measurements, it's part of our curiosity to set up measurements, but it's step back to make sure that those measurements are doing what you think they're actually doing. Test them, measure, evaluate them, and always check the measurement error. I found so many projects that it was simply the gauge that was causing the problems, not the product. And then conduct experiments. Now, this includes doing accelerated life testing, for example. That's an experiment. It includes working with a design team to optimize the performance of a product, but minimize the failure rate or its robustness to the environmental factors. That could be a design of experiments. We do experiments when we're projecting what's the field failure rate going to be over the next 6 months. That we do an analysis, and we then gather data as the next month data comes in to check whether our projection was correct or not. We do comparisons. We look at different vendors. We look at different design options. We consider vendor data and judge their experimental work. Is it meaningful or valid or not? The idea is that we have a broad range of tools available, both statistics and in the lab, in order to run experiments. Now, the critical piece here, and it's all too often not taught well in school, we get taught the scientific method of how to set up an experiment. Yet the hard part is, well, what question or what hypothesis do we have? So don't forget that part. Set up a good hypothesis, one that your experiment can have a reasonable chance of unquestionably showing it works or unquestionably showing that it doesn't. So if I have an experiment, are we ready to ship? And we do a sequence of different tests against different criteria in order to peel away some of that uncertainty. It's a set of experiments we're running. If we only do this on one sample overall, and we're going to make 100,000 of these things, how well do we really know? I'm not saying that it's impossible to make that work, but how well do we know this? How well does that experiment inform the decision maker for that question that's being posed, right? If we know we got variability in our manufacturing process, then 1 or 2 samples is probably not going to cut it. If we know that the variability is very, very consistent or very small, 1 or 2 samples might be all we need. Yet take that extra step, make sure that anything you run, any experiment or test or evaluation you do, is set up so that you actually can get a result that's meaningful. If the result is, well, we ran 3 samples and they worked for 2 weeks, but we know nothing else besides that, then it's not terribly useful unless your product is only expected to work in that exact environment for exactly 2 weeks. Otherwise, it's hard to extrapolate from there. So set up your experiments carefully, and that's an essential skill for us. You've heard me say this a number of times over the years, is everything fails, right? But I also say that design is where reliability happens. The reliability engineer can influence the design and the decisions made in the design process. But the old days, I hope, doesn't exist in your organization, where somebody creates a product or a design and they hand it over to you, say, now add reliability to it. Well, that doesn't really work, right? There's not a lot we can do when the design is finished and not willing to be changed. We can judge its reliability performance under some criteria, but that doesn't mean that you add reliability to it. You're just quantifying it. If we want to create a reliable product, that happens in the design. And so an essential skill for us is to understand that concept, is that all of this DFR stuff that we do, of influencing design teams so that they get the feedback they need to make decisions. They get the guidelines and techniques and information available to help them make good decisions. Then they can design a better product, right? it's all based on how well our design teams trust the reliability information that they're getting, whether that's a derating guideline or a prediction of the design's performance or an estimate of the future performance. The idea here is we can help create that list of what could go wrong. FMEA, for example, we could peel away at what we don't know using HALT testing and similar tools, and we can estimate the reliability using physics of failure and prototype testing. We can do lots of different things, but if those are just done and not influencing the design team, we've lost that opportunity. But if they understand the data that we're presenting, they understand the value of doing derating or stress strength analysis, for example, and how to interpret a physics of failure model, then they can, the design team, the people making the actual decisions, can actually make better decisions. And that's what we're really, really after in the DFR process. Now we can schedule a FMEA and they go do it and check it off the list, but unless any actionable behavior, visible behavior changes and changes to decisions happen, it's just a fun meeting, maybe we got some pizza. In order to make it valuable, we have to understand the challenges that they're facing, the constraints they have, and what information they need. And then that goes back to that presentation skill set that we need to do. Now, as many of you know, suppliers in our supply chains are incredibly complex. And I don't have a hard number on this, but I'd say a third to more of our field failures are from anomalies propagated through our supply chain. And the hard part is we don't have time to go after every supplier and every supplier's supplier, tier 3 and so on. Yet we can use the various tools and the risk assessment tools we have to narrow that process down and do the due diligence in detail work on the ones with the highest risk, and then monitor and maintain systems that keep an eye out for variations that are going to harm our product's performance in the future. So our ability to do design for reliability extends throughout the supply chain. And it gets more and more difficult the further we go, yet it's a relationship. It's not a show up and audit them when something goes wrong. You're way behind the curve at that point. And finally, customers. The idea here is that customers don't go to the lab and only test high temperature for your product and go, oh yeah, it works. No, they put it to use. It may have temperature and vibration and salt and fire ants and half dozen other stresses that we may or may not have considered, and they're all simultaneous, right? Now, if our product is designed well, that we're robust to all of those combined stresses. And that customer then experiences a product that provides the function they paid for, and they get value from that. Yet we don't always know exactly what environment they have. So part of our work is understanding how customers use our products and why they use our products and what values do they derive from the products. What's the pain that they have when a product fails? What happens at that point besides dealing with customer service on the phone? The idea is to constantly work with your customers in as many different facets as you have access to fully understand their relationship to our product with the facet of product reliability, from our point of view anyway. But it extends beyond that. It informs not only our current products and failure analysis of existing failures and our improvement efforts from those, but it also informs how we design and build our next product. And it also may spot, as Adam Barrett talks about with use case 7, it may identify a new market opportunity. Customers using our products in unique ways may become a whole new segment for our products in the market. The idea here is that our customers are what we're building the product for, and it's so that they can exchange some cash, usually, with us so that they derive a value from it. If it fails in full or partially, they don't get as much value. And that's where the rub is, right? That's where the bottom line is. So our effort is not just the halt chamber. Our effort often has to include a really good understanding of our customers. All right. So I mentioned, I don't know, half a dozen or so here for you. Which techniques do you think are considered? What would be your number one or two techniques that either you would say are essential, maybe I missed those, or that you would say after listening to this, yeah, I got to get that right at the level of it. Yeah, I like your comment, Sean, about fire ants. I actually worked with a product team that fire ants were a significant threat. It was in-ground power meters that had a very small electromagnetic field about them. And for whatever reason, it was the right kind of stuff that allowed, that attracted fire ants. And they would eat through insulation and all kinds of stuff to get closer to the field. And so they would create all kinds of havoc with their products. And there's actually a lab, there used to be years ago when I was working on this project, lab in Austin, Texas that did fire ant testing. And so, yeah, I didn't want to go work there. Yeah, Brian, excellent point. I didn't talk about that, is learning from your competitors. You know, even in their advertising, what are they featuring? What are the elements that they're recognizing that their customers want? If you can get a hold of their products, which many types of things we can just go buy, and do a teardown analysis. How did they solve the problems that we're facing? What tools, techniques, materials, whatever did they use to solve a problem? And what's working and not working? Usually a quick step then is to look for patents so we don't get too much trouble. But if we're using plastics and they're using metal, why did they do that? What were the stresses or elements that led them to make that decision? So always a good thing to do is look at your competitors. CRO-AMSA, that's a specific tool or technique. It's a reliability growth modeling. And yeah, I didn't mention it as a particular one. It often goes towards planning and test planning, but also towards that mathematics. Are we on track? Are we going to make our goals or not? And what's it going to be? David's going DFMEA and failure analysis. Yeah, I'd broaden that to risk identification, prioritization, and understanding what happened. But yeah, those are very common tools that we use all the time. And it should be second nature, even if it's not a formal FMEA process or formal dedicated resources for an FA. The concepts in those should be key techniques we use all the time. That's data analysis, FMEA, and RCA. Good. I like them all. I'd expand each of those, as I mentioned above, from data analysis into just general mathematics and statistics. Good. All good tools. There's a lot we do, right? There's a handful. I had a colleague years ago gave me a list of over 400 techniques relevant to reliability engineering. I'm like, oh, okay. I didn't know we had to know so much. We don't. We need to know mathematics, and that allows us to do all kinds of different techniques and tools, specific tools. We need to do risk identification and management, right? FMEA and a slew of others fit into that one. We need to understand the physical world around us, and sometimes the software world, of how that works. And it's failure analysis and being curious and running experiments and understanding phenomena, measurement systems, and so on. I break it down to like 5 or 6 different things that we fundamentally need to know and apply with finesse so that we add value. So remember that we focus on influencing decisions. We have a range of different tools that we use on a regular basis. They all involve, to lesser or more degree, our ability to influence, our ability to explain, inform, transfer understanding, all those kinds of things in our ability to convey the results of the math we're doing, the results of the failure analysis, and the influence specific activities have on a design and on its performance. We have to be able to convince others that these things are of value, and then help them understand how that value shows up. And the idea that all these different range of things we do, all the different tactical things we do, when you put them in the context is that it helps somebody make a better decision, I think helps us focus on what's important to be done. And then along the way, we're constantly learning how to use different tools, whether a different kind of regression analysis or a different kind of failure analysis technique or a different material set and how it behaves in our design. It's one of the things I really like about our profession is that we don't have an infinite number of brand new, fundamentally new technologies impacting design for impacting reliability engineering. We have lots of different materials and lots of different inventions and lots of different things that can fail. Yet the tools, math, and understanding and design practices remain pretty much the same because they all influence our ability to make decisions. And so that's how I wrap up the essential techniques is, well, I could repeat it again, but I won't. I think we just got out of time. So let me see if there's any questions. I'll wrap it up here, and I'll stay on the line. I know we're right at the end point. I'll stay on the line if there's any questions or comments. And I, as usual, have completely forgotten what I'm going to talk about next month. I did ask before starting about topics, and accelerated life testing was an idea. I'll have to play with that a little bit, see what we can do. All right, is there a single book which comprehensively explains all about the modeling tools you mentioned in your slides? You know, see that, Stan? Srivatstan? I'm sorry if I'm not pronouncing that right. It's a good question. I don't know of a single book that covers physics of failure to fault tree analysis. I know there's a handful of books that do a high-level overview of some of these things, but not a comprehensive one. There are books on physics of failure. There are books on modeling and different tools. There's obviously statistics books on regression analysis and so on. You know, the closest I would come to that is the one by Chris Jackson that he has up on Amazon. And I'm drawing a blank on the title of it. It's also up under on Ascendo underneath the Ascendo authors under books, under resources. Yeah, it's a pretty long tome and it covers a wealth of information. So it's probably the closest I know of that gets into enough detail on a lot of the stuff. All right, welcome day. Please do a session on risk-based inspection. I've heard that term. I've probably done something similar to that. I'll have to dig into a little bit more what that is and add it to the list. It'll be something I can learn. I get the idea is that it is, instead of saying we're going to do a lot sampling and 10% of each lot coming in, or you know, looking at this, that, or the other thing on a fixed schedule, is modify that based on the amount of risk that it has. And then we can define that in a good number of different ways, I imagine. It's a good idea. All right, you're all welcome. Have a great rest of your Tuesday. And thanks for attending. I hope to get the recording up within a few days and look for an announcement later this week about what we're talking about next week. A couple of weeks from now, Chris Jackson is back. He's going to be talking about some of the details around how to do Markov chain Monte Carlo, which he introduced in his last one. Immediately after in the presentation, there were a lot of people looking for more details of how to do it. And so he's coming back with some more details on that. And so that's in 2 weeks. And I've also got a couple new presenters coming in that are scheduled into October, maybe even into November. So going to see some new voices online here. So thanks again to everybody that was able to join today. And if you're watching the recording, let me know if you have any questions. I'm always available to respond to those. And you can find us on email and on the About pages and so on, and LinkedIn. So thanks again for everybody. Enjoy the rest of your day. And at least if you're in California, stay cool. It's going to be another warm one for us out here. All right. I think we'll wrap it up here. Thanks again.